Okay, good morning. Welcome to yet another session of Intro to Photonics. We started this particular module several lectures ago. We said we are going to identify the fundamental principles of photon interaction with atoms and specifically analyze light generation and amplification. So, as part of this, what we have been considering is amplification of light. And then, with respect to the amplification, we said, okay, we would typically deal with a 3-level system or a 4-level system, right, like this. And then, in terms of analyzing such systems, we said we will first of all start with the rate equations, right. We learned how to write rate equations, and then we will assume a certain condition. What condition? Steady state condition, because that's the condition we are typically interested in. And we said if you assume steady state condition, then dN2 over dt and dN1 over dt are equated to 0. So, that allows us to come up with a relatively simplified expression for the inversion, and we are trying to get that inversion as a function of the pumping rate as well as as a function of the amount of signal photons that are going through the amplifier. Okay. So, what we are going towards beyond this is, we start from an amplifier and then how can we build a laser from this. So, we are going to start incorporating feedback, and then we will say how to get a laser based on this amplifier. Maybe that is what we will start doing from the next lecture onwards. But for today, I thought we could just see how well equipped we are to take up a practical problem. Okay. So, for this, I thought it would be a good idea to go back and consider this quiz problem. This is actually quiz 2 last year or the year before, in 2016, right. So, this is quiz 2 paper, and then from that paper there is this one question on amplification using a erbium doped silica fiber. So, let us see if we are equipped to handle such a question. Okay. So, let's take this example and see how we can do this. Okay. And before we get to that, I just want to give you a general idea of a construction of an EDFA. So, some of you did an experiment with EDFA. You constructed an EDFA and you even demonstrated that you could get light amplification using this erbium doped fiber amplifier. But let us just look at this in a little more detail than what we have done so far. So, what we need as far as the EDFA is concerned is clearly the erbium doped fiber. So, let us say I have an erbium doped fiber that is spliced with some other fiber with regular undoped fiber. So, this is erbium doped in silica. Okay. So, to make an amplifier with such fiber, what all do we need? We need to send in the pump, right. So, you have the pump radiation coupled into this, launched into this erbium doped fiber, along with your weak signal radiation, right. And the pump is getting absorbed along the length of the fiber, and maybe some of the pump still remains after this length of the fiber. You may want to remove that. So, you use one more fiber coupler. These fiber couplers are called in short WDMs. It stands for wavelength division multiplexer. Okay. So, in this case it is actually on the input side, it is combining two different wavelengths. The pump radiation at 980 nanometer is combined with the signal radiation, let us say at 1550 nanometer. Okay. And on the output side, you have a strong amplified signal at 1550 nanometer, and then you may have some residual pump radiation that you can probably remove using another wavelength division multiplexer, which is actually doing a demultiplexing operation, right. It is separating out two wavelengths. We will not go into much detail on the wavelength division multiplexer right now. It's we can come back and look at that in more detail later on, but let us just focus on the amplification process. Let us try to understand what exactly is going on in this structure and how light gets amplified. Okay. So, let us say this is the length of this amplification region, and let us try to figure out what all is happening over here. So, this is 0, and let us say the length of the amplifier corresponds to L. So, let us say this is the propagation direction, which let us call that as Z direction. Okay. So, let us first track how this pump radiation is going to be distributed in this, right. So, the pump radiation is launched from this point, let us say Pp of 0 corresponds to the pump power that is launched into the fiber, okay. And within that fiber it is getting absorbed, that pump radiation is getting absorbed. So, you can say that dpp over dz as it propagates is going to go through a certain absorption at the rate, let us say alpha p, that is the absorption coefficient, multiplied by pp. So, it is actually getting absorbed at a constant rate. So, what is the solution you expect? So, it should be the solution for this is an exponential, right. So, you would basically say that this is getting exponentially decaying. So, that is given by that rate at which it decays, it is given by exponential of minus alpha p multiplied by z. So, what does that mean? What does that mean as far as your population inversion is concerned, right? Let's think about that for a second. So, what we have, let me just for simplicity just consider this two energy levels. We do have a third energy level in erbium, right? So, we are not paying attention to that. So, you have a very high pump power at the beginning of that fiber. So, what can you say about the inversion that you have there? So, there will be a lot of ions, this erbium ions that are going to the higher energy level compared to what we have at the lower energy level, right. Now, what can you say about what is happening over here? Here the pump is actually much lower. So, correspondingly the inversion that you expect is going to be much lower. So, here you may have very few erbium atoms, or erbium atoms in silica actually are sitting in an ionized form. It is a triply ionized form. So, if you want to be really rigorous about it, you would actually mention them as erbium 3 plus. Okay, that is how things. So, it is common to say that what we are considering are erbium ions instead of erbium atoms. Okay. But nevertheless, what this tells us is this inversion is not constant in a real amplifier. If you want a constant inversion, what would you do? What would you have done? Pump from the side, right? So, if you actually sent in pump radiation from the side of the fiber, if you pumped it from here, you could have possibly maintained constant inversion, uniform excitation, right. That is not possible, or I should not say it is not possible, it is highly challenging to implement for an optical fiber, because the optical fiber itself, the telecommunication fiber that we use is 125 microns in diameter, out of which the core region in which the erbium atoms are doped into, those correspond to only a few microns. So, you are not going to be able to efficiently focus all your pump light so that they are absorbed in the erbium fiber. So, because of those reasons, you choose, as far as fiber form is concerned, you choose to pump from one end. Now, the situation may be very different if you are talking about some erbium crystal, right. Erbium actually doped into a crystal, a glass crystal, a bulk glass. So, you can probably have a cylindrical glass rod, for example, in which this rare earth ion is doped, and you can excite it from the sides. In fact, you can put it as part of a cavity, some mirror around it, and then you put some your pump on the side of your rod, and you can pump it so that it either directly is incident on the rod, or it goes and hits the mirror and then it is absorbed by the rod. So, you could have something like this. This is your, let us say, erbium crystal, and then you could have mirrors over here on either side of that, and then you could have your pump from this side. So, it either goes directly into this, or if the pump is going this way, it is deflected back into the rod, So, there are different configurations with which you can achieve this, but the idea here is that you would have to go to some crystal or bulk glass sort of configuration or form, so that you can achieve uniform excitation. If you are doing fiber based amplifiers, you invariably have to pump it from one of the ends of the fiber. Okay. I said one of the ends of the fiber. So, you could possibly launch the pump from the output side, right, and take out the residual pump from this side, from the side where you are launching the 1550. So, that would actually be called counter pumping sort of configuration. So, the question is, how would that help? Actually, that is probably a preferred configuration. Why? Maybe I'll just hold on to that question, hold on to that thought for a minute. Let me just complete what I was going to say here as far as the signal is concerned, and then it will become obvious. What do we have as the signal, right? So, there's one more question, yeah. The fiber is only 125 microns thin. So, that is the size of your hair, right. So, and within that the erbium core is only a few microns diameter. So, if I launch light, if I have the fiber here, what are the chances you are going to have that light absorbed? Okay. So, of course, you can focus that light, you put a lens and you focus that light, and then you have to focus it into a very thin line. You have to hold your fiber straight and you have to have a very long focus line, all of that, right. So, when you actually try to do that, you find it's quite cumbersome. Suppose to a rod, this rod can be a few millimeters thick. In that case, and it's a relatively short rod, so you can actually have these pump diodes stacked along the rod, and they are all pumping like this. So, in this case, we are saying that the rod in 3 dimensions would look like this, and so you could have these mirrors on either side, and then the row of pump diodes which are directly pumping the rod. So, you would actually have fairly good efficiency with which you are absorbing all that pump radiation. So, the question is, so aren't we actually having difficulty in focusing light within that optical fiber itself, right? And that's certainly a valid question. That is actually saying, if you can do that, can't we do that side pumping? It's not the same, because if you are doing launching light into the fiber, you are doing it only at one point. You are not trying to keep the fiber straight and maintain that focus all along the length of the fiber, right. So, you are launching at only one point. And how do you launch light into a single mode fiber? You have already done that, right. So, you know how to launch light into a single mode fiber. So, that is quite straightforward. And I would also want you to consider this other thing, which is light, when you are pumping at 980 nanometer, where does that light come from? That has to be laser radiation, right. So, you have, because your absorption peak is relatively narrow, it is not a very broad absorption peak. So, you have to come in with a laser and excite these erbium atoms. And when you consider what type of source you will use, you will find that you are typically using a semiconductor laser diode, okay. And the next few weeks, we will actually go into the details of the construction of a semiconductor laser diode. And what you will find is that the aperture from which light is emitted in a semiconductor laser diode is in the order of a few microns. So, you have the possibility of taking the fiber. If this is my semiconductor laser, I take my fiber and just directly butt couple it against my semiconductor diode, right. So, I just hold it right against that aperture, so I can couple light directly. I do not even have to think about taking the light out and having some focusing optics and coupling it, because the packaging, that would be a mess, right. So, instead what people do is take this fiber directly hold it against that output aperture of the semiconductor laser, and then you glue it and all that, and you put it into a hermetically sealed package and you are done, and that can stay for tens of thousands of hours, there is no problem. Okay. So it is much easier to come in with that pump radiation in a fiber form and couple into it, but like I said, this is what happens. Now let us go back and see what happens to the signal. What do you think is going to happen to the signal? Signal is going to increase, right, and it is going to probably go through an exponential increase to the point that you have fairly good inversion. In the case of erbium, if you do not have inversion and you have a lot of signal photons, what happens? In this region towards the later part of the fiber, you have very little pump light. That means very few atoms are actually excited to that higher energy level. So, most of them are sitting in the ground state, and then you have 1550 nanometer photons coming through. So, what is going to happen? What is more likely to happen? Stimulated absorption, right? Because there are not too many photons, too many atoms in that excited state, everything is in the ground state. So, the probability of actually having that absorption event, so you have here 1550 nanometer radiation come along, and that energy difference corresponds to 1550 nanometers. So, you have absorption of that light happening. So, you have what is called reabsorption of that light happen beyond a certain distance, and then it might actually beyond that distance, if you have longer fiber, you would lose signal photons. Okay. So, this process is called reabsorption, and reabsorption is a major issue in 3-level lasers. But what can you say about this in a 4-level laser? What can I say about reabsorption in a 4-level laser system or amplifier system? So, we are considering stimulated absorption as this process, right, going from the lower energy level to the higher energy level. But in this case, what can you say about atoms in that lower energy level? Very few atoms in the lower energy level, because you have a fast non-radiative transition relaxation that is happening. So, everything is going to the ground state. So, now if I come in with, in this case 1064 nanometer radiation, very little absorption is going to happen. So, you do not have this issue of reabsorption in a 4-level system, you do not worry about that. Okay. But in a 3-level system, you have to worry about it, because if you are not exciting your rare earth atoms, they are all sitting in the ground state and they can actually reabsorb the signal. Okay. So, that is something to keep in mind. Okay. So, there is a question of optimization of your length, right. There is a question of optimization of the length in the sense that if you have such a long length that you have very few pump photons towards the later part of the fiber, it's actually not helping you. So, you have to do some modeling to see how your absorption is happening, and for a given pump power. So, you typically consider the maximum pump power that is available to you, and for that pump power you see how much is going to be your inversion at the farther end of the fiber, and then you say, okay, that's, I'll cut off the fiber at that particular length, so you don't have so much reabsorption effects. So, the question is, can we actually re-energize the erbium dope fiber at that particular point, and that will be a very good idea, right. So, you could think about re-energizing the fiber at that particular point. In fact, what could be done is, instead of just pumping from one end, why don't you pump from both ends? Okay, and that would be a very good idea as well. So you can actually keep your excitation level relatively uniform across this fiber. Okay, so that's called bidirectional pumping. So now we are starting to look at some advanced issues in advanced configurations. I'm glad you guys are thinking like this, but that's what you need to do to have uniform excitation, and that's a good way of making sure reabsorption is not happening. But the other point about counter directional pumping, let's examine that. If I am launching my pump from this direction, right, then I have very high inversion at the later part of the fiber, and I have very low inversion at the front part of the fiber. And that works out very well. Why? Because when you have the weak signal launched from the left side, right, there are very few signal photons coming in. So they need very few excited atoms to achieve the gain. They need very little inversion to achieve gain. And as they propagate towards the right side, your signal photons are getting multiplied, and they need more excited atoms, more inversion, right, to sustain their amplification. So you would say, from the perspective of utilizing your inversion efficiently, you want to do counter directional pumping. Okay? So the pump configuration that you would be doing in your laboratory this week, just pay attention to that. That is actually counter directional pumping. So the question is, in counter directional pumping, reabsorption doesn't happen. The chance of that happening is very low. Of course, you can argue that if my pump excitation is very low on the left side of the fiber, then you have more atoms in the ground state versus this thing. So the few photons that are coming in, they are getting absorbed, right? So what you have to ensure is that you maintain a certain level of inversion. So you don't, once again, it doesn't mean that you can, in counter propagation direction, you can make the length arbitrarily high, long fiber. You still have to cut off the fiber so that the already weak photons don't get lost, in that absorption. So those are all, like I said, fairly advanced issues that you can get into, and you can look in a lot more detail, but maybe as far as this course is concerned, we won't go into so much of the specifics. But I will try to equip you to evaluate these conditions in a little more precise manner. Okay, so that's what we'll try to do now. Okay, so the question is, what is this dependence? How does that signal gain as a function of length? How do you evaluate this? Now, to evaluate this, you actually have to consider one particular point which we have so far sort of neglected. So when we were looking at these rate equations, we made one assumption, okay, which is actually not, practically speaking, it's not correct. Okay, what is that assumption? So we used the same when we were looking at stimulated absorption and stimulated emission, we use the same rates Wi, okay, and Wi we defined as phi s multiplied by sigma E as far as emission is concerned, right. So, this is phi s sigma E, and this one is actually phi s sigma A, right, and we are actually considering the signal photons. So, I will superscript with S. So far we have assumed that sigma E equals to sigma A, okay. That allowed us to get some more insights into this amplifier system in a simplistic manner, but time has come now to get rid of that assumption, okay. Let's actually look at how sigma E and sigma A would be, and for that we have previously considered this erbium absorption and emission cross sections, right. And what do you see here? What can you say about sigma E and sigma A? They are not typically equal. In fact, there is only one particular point where they overlap, and you can say, okay, at that particular point around 1540 or something like that, 1535 maybe, at that particular point they are equal, but in general they are not equal, right. And what this also tells us is the absorption process is more probable where? At shorter wavelengths, and emission process is more probable at longer wavelengths, okay. So, you are more likely to get gain in longer wavelengths, okay. That's something that we were observing later on, but as far as how the signal is getting amplified, now we have to consider this in a little more detail, okay. So, we will look at this. Now, what we want is, at this point is Ps of L, we want to know what is the gain that you have in the system, which is given by Ps of L over Ps of 0, okay. So, to evaluate that gain, we need to now understand how this amplification is happening. So, what is the gain at any particular point along this fiber? So, what I have to track is the signal power, or I could actually track the signal flux, because this can be written as phi s of L divided by phi s of 0, okay. That is the signal flux that is coming into the fiber, and then we have a signal flux that is going out of the fiber. What we can do now is, as far as the signal flux is concerned, right, I can write an expression for d phi s over dz, because that is what is describing how my signal flux is varying along the length of the fiber, and that I can write as N2, I will not use Wi anymore, because I want to bring out the fact that sigma E and sigma A are different. So, I would have to write this as sigma E at the signal wavelength right, multiplied by phi s, okay. Phi s is photons per second, okay. The small phi s we are using as photon flux density. This is the larger phi x, the capital phi s, okay, which corresponds to photon flux, okay. So, this minus the stimulated absorption term, which I would write as n1 sigma a s phi s at that particular point, okay. Now, you have to remember this, which are constants and which are variables in this expression. Which are the constants? Sigma e and sigma a, right, they are constant for a given amplifier system, whereas everything else is variable. So, I actually, if I were to write it out properly, I would say n2 of z and then phi s of z and n1 of z phi s of z, right, you understand that. And what determines n2 of z and n1 of z? Certainly it depends on the total amount of doping that you have done, but what else? The pump excitation that you have at that particular time, at that particular location, right. So, that is what makes this a little more interesting. So, since I can write Ps as phi s multiplied by h nu, right, energy over time is power, right, and flux is 1 over time, 1 over is in 1 over second. So, h nu is I would say h nu s, because that corresponds to the signal photon. So, the signal photon energy multiplied by the flux gives me power. So, I can just write this as dPs over dz equal to Ps multiplied by n2 sigma Es minus n1 sigma As, right. So, yes, so I instead of writing in terms of photon flux, I am writing in terms of photon power, right. So, the signal power Ps, okay. So, instead of phi s I am just substituting Ps, okay. So, if we look at this, and I can write the overall gain now based on this. I will just go over to the next page for that. So, my overall gain, which is given by Ps of L over Ps of 0, is now going to be exponential of this factor. You have n2 sigma E s minus n1 sigma A s, right. But this is not a constant now, right. So, when I want to look at the overall gain, what do I have to do? I have to integrate under that curve, right. So, I would have to integrate from 0 to L dz, okay. This entire thing now is sitting within an exponential. Do you understand how I wrote that? Just go back to this. So, the solution for this is going to be an exponential, right, and since we have just a positive sign here, we are just saying exponential of this, but what we are interested in, that is the solution of Ps of z, What we want is PS of L, right. So, PS of L, if you want to figure out, then that I would have to basically look at that how it is accumulated over that entire length. So, I have to integrate over that entire length to get this. So, if I want to have a gain coefficient, right, a gain coefficient at any particular point, this would be my gain coefficient. This entire thing now is my gain coefficient, which we previously said corresponds to gamma of z. But if I want to find the gain, the overall total gain, I will have to integrate the gain coefficient over that entire length, right, and that's what we are doing. Previously, when we were discussing this sort of a case, what we did was we assumed uniform excitation. If there is uniform excitation, N2 of z is actually a constant, you can just say it's N2, and N1 of z is constant N1, and so that integral will yield you what? Integral over dz will yield you just L, right. So, we just multiply this by L. So, I can make a special case here, say for uniform excitation case, I would just say G is exponential of N2 sigma Es minus N1 sigma As multiplied by L. Okay. Do you understand this? So, for uniform excitation it will be like that, but for if you want to consider the fact that you are launching maybe from only one end of the fiber and then you have exponential decaying pump, then you may have to deal with this sort of a situation. Okay. So, this also tells us something very, very important to realize. If sigma Es, the emission cross section, is greater than sigma As, okay, mathematically you can say that N2 need not, or maybe I will just emphasize that, need not be greater than N1. Does that make sense? To get gain, what you need is that the gain coefficient be positive. That entire value needs to be positive, right. So, it does not mean that you necessarily have to have N2 greater than N1. You have an inversion, but in these regions over here, right, you have sigma A is almost 0, sigma E is a finite value. Okay. In those regions, N2 need not be very high compared to N1, it need not be greater than N1. N2 can be a fraction of N1 and you can still get gain, right, because what matters is that this factor overall is positive. Okay. So, conversely, I can also say that sigma Es, if it is less than sigma As, right, if the emission cross section is less than sigma As, that does not mean that you cannot get gain. Normally you say, oh, absorption is higher than emission cross section, so you cannot get gain. No. What it all just means is that sufficiently high N2 over N1 can provide gain. Okay. So, if you just have if sigma E is less than sigma A, you just need to overcome that with a higher fraction of these rare earth atoms in the excited state compared to what is in the ground state. So, that is the question. You need population inversion for lasing to happen in the case of sigma E equal to sigma A. So far we had been saying that, but inversion, the definition of inversion we are slightly modifying, right. We are saying that the inversion is not just number densities, you have to factor in that cross section also. Okay. So that's where we are, and I see I've run out of time. I will continue this in the next session.